Hello everyone, welcome back to lesson number 41. We're in BC Calculus and today we are continuing on with sequences. In the first video we talked about whether a sequence converges or diverges, and we determined that in order for a sequence to converge, the limit of the function has to exist when n approaches infinity. So these first 6 problems we did on the first video, and so we're going to go ahead and go to these 6 questions. And so if you guys look at example number 12, we want to know, does this sequence actually converge? So we are going to find the limit as n approaches infinity of this function, the natural log of n over n. And one of those things that, I talked about in the first video, functional dominance. So is the numerator functionally dominant? Is the denominator? Meaning that which one goes to infinity the fastest? Well, that may be something that we're not really comfortable with the natural log. So, L'Hopital is like a really good way of figuring out how to do these problems. So if you plug in infinity, you get the natural log of infinity, which is infinity. This obviously is infinity. So infinity over infinity means that we can go to L'Hopital. And then we go and take the derivative of the top and the bottom. And so we get the derivative of natural log of n is 1 over n. The derivative of the n is 1. So we're going to take the limit, and then this just means being 1 over n. Well, this is a functional dominant problem because our denominator has a higher degree than our numerator, right? This graph is actually going towards 0 because this is a graph of 1 over x, right? So 1 over x looks like this. And as we're approaching positive infinity, we're going to 0. So since this limit of this function is equal to 0, then we can now say that this function converges. So more specifically, this sequence, because again, we're going to talk more about series in the next set of videos. So for this one right here, guys, it's pretty easy to kind of figure out what this one's doing. Yes, we can look at the limit as n approaches infinity of some number to the n power. Well, you can already see that when we plug infinity, we're just going to get infinity, right? It's just pretty straightforward for this. So this one's definitely going to diverge. Another thing that you could do if you wanted to for this problem is to kind of see what's going on. Well, when n equals 1, we're going to be at 2. Then when n equals 2, we're going to be at 4. And then when n equals 3, we're going to be at 8. And then n equals 4, we're at 16. So you can see that we're going to keep going up and up and up to infinity. So there is no limit to this sequence. So obviously it's going to diverge. Now on the flip side of this, we could do a couple of things. We could actually say, well, let's look at the limit as n approaches infinity. And you can start plugging stuff in. But we can also see it's the 1 to the n over 2. To the end. And this is again where I talk about functional dominance, because this right here, this is always going to be 1. And this is going to be 2 to the first, which is 1/2. Then, if I plug in 2, I'm going to get 1 over 4. I'm going to get 1 over 8. So again, you guys can think about it like this. So when n equals 1, I'm at 1/2. When n equals 2, I'm at 1/4, 1/8, 1/16, 1/32. You guys can see again that the denominator is functionally dominant. This is functionally dominant. This is going to infinity faster than the numerator is. So that means that this limit is actually going to be equal to 0. Therefore, this sequence is going to converge. So using the logic that we just did in examples number 13 and 14, you guys can see that for this one, the limit as n approaches infinity, and you guys can see it's getting repetitive, right? So I can rewrite this if I wanted to as e over 2 to the n power. Well, if you guys look at this one, e is actually greater than 2. Right, e is 2.7 something. So e is greater than 2. So that means that my numerator is actually approaching infinity a little bit faster than my denominator. Since that's the case, this limit is actually equal to infinity, which we really just say does not exist. So therefore, this one is going to diverge. So it's all about the functional dominance for some of these problems that you're going to see right here. So let's look now at our next example. So for this one, ladies and gentlemen, and we actually talked about this example in the previous video, the limit as n approaches infinity, and then we get negative pi to the n power all over 4 to the n power. So we can actually say that these are all to the n power. It doesn't matter, it really doesn't matter if this is positive or negative. All we're really looking at is comparing the two numbers together. So pi and 4, well, 4 is obviously going to be greater than pi because pi is 3.14. So since our denominator is functionally dominant, then this is actually going to be equal to 0, and this is going to converge. A visual of something that looks like this, because sometimes students want to see that, the visual that I'd like to show for these problems is, yeah, it could be like positive 1 here, and then like negative 4/5. and then positive 2/3, and then negative 1/2. So you guys can see that the sign around it doesn't really matter as long as it's going to get closer and closer and closer to 0. So this sequence is actually going to go to 0. So we're not really necessarily caring about the signs for these problems. We really just care about the actual values themselves. And this last example, ladies and gentlemen, we talked about this one before. This one takes us way back to L'Hopital as well, but these other indeterminate forms for this. So we want to find this, this one. Now, a lot of people already know that this ends up becoming e, right? This is the function for e. But just a little refresher for you guys. This is one of those limits where we want to set equal to 0 because we get 1 to the infinity. And 1 to the infinity is one of the indeterminate forms that you guys learned a long time ago. So what you guys remember doing is adding the natural log to both sides. So we're just doing a little review here. We add the natural log. So remember that this limit now, we're looking at the limit, and then our answer is going to be the natural log of y, not the actual value that we're looking for. So then the next step we would do is we would pull the n down, right? So we would pull the n down in front of the natural log, and I don't want to show every single step here, so I'm going to just go ahead and write it like this. So n would come down here, and then what I would end up doing is when n is here, I would then bring it to the denominator. So when I bring it to the denominator, then I would actually have n to the negative 1. And this is what we did when we do these problems. If we were not comfortable with this, is actually e. And so when we do this problem, again, I'm going to erase it, and well, n to the negative 1 is actually just 1 over n. And so we plug infinity to this, we're going to get the natural log of 1 plus 0. The natural log of 1 is 0, and then this is going to be 1 over infinity, which is 0. So we're going to get 0 over 0. So this is the indeterminate of 0 over 0. So then we're going to continue with this one, and we're going to do the derivative of both top and bottom. So the derivative of the top would be 1 over 1 plus 1 over n times the derivative of this, which would be negative 1 over n squared. And then the derivative of 1 over n is also negative 1 over n squared. And so what awesome thing happens here is that this cancels with this. And so I am left with the limit. I'll go ahead and write it right here. The limit as n approaches infinity of 1 over 1 plus 1 over n. If I plug in infinity now, I get 1 over 1 plus 0, which is 1. So I get 1. So the limit is 1. But remember, our value we're looking for is 1 is equal to the natural log of y. Well, again, I told you guys that this is already in the form of e, so y actually ends up being e, which means that this whole limit of our function, the limit of this function, 1 plus 1 over n to the nth power is actually e. Therefore, this sequence will converge. The sequence will converge. Okay, so that is basically examples for when a sequence converges. And just to sum it up again, ladies and gentlemen, when a sequence converges, the limit has to simply equal some value for L. Like it just has to be equal to some number. If that sequence does have a limit, then it will converge. Any other case, it doesn't, and it diverges. So that's going to be the end of this video. We will come back and talk about monotonic sequences in the next one, and I'll see you guys then. Take care.